So what we're going to do today is we're going to use our graphing calculators and graphing to help us figure out domain and range. For the most part, the domain you should be able to do without your calculator, but the range part is sometimes difficult to see just from the equation. So, first thing we're going to do is we're going to go to our graphing calculator and we are going to type in this equation. Also, if you borrowed one for today, I'm hoping you have one at home. If you don't have one at home, you do need one for this course. So the options are either you can rent it, but then you're renting for both semesters because you rent per semester, or you can purchase one. The school does have some for sale, but you can also look online in other places too if you'd like. Yeah, you will need your own calculator for this class. So what you were going to do is you're going to hit the y equals, and you're going to type in 2x squared. Was it plus 4x? Minus. Oh man. First, if you're not familiar with the calculator has a subtract sign and a negative sign. And probably the number one mistake is sometimes people want to write -3 plus something and they hit the subtract sign and then the calculator is confused. So they are different buttons on the calculator. One of them is a negative sign, one of them is a subtract sign. And then if you go and hit graph, I'm going to pick my colored. Does it let me do it? Oh yeah, there we go. Oh, but I got to retype it in. I'm picking the colored one. Oh, because I feel so. And you go and hit graph, and it looks like this. Now, the reason you can figure out the domain, which is everything, without a calculator, is looking at the equation. The domain is your x values, and often you're thinking, what x values are allowed? And at the same time, you're thinking, are there any x values that are not allowed? Is there anything that I could put in for x that mathematically would cause problems? And for this, there isn't. So if there's nothing problematic, your domain is always going to be everything. And you can write it with round brackets as negative infinity to infinity, or you can write it that x is an element of the real numbers. So that is a little bit of a review. But in order to figure out the range, it's a little bit more thinking to do. So we would need to know how low does it go. From the graph, it definitely looks like it hits a minimum at -2. And if we look at the range, sure enough, it is -2 to infinity. -2 is included, so we have those square brackets there. But just eyeballing the graph, how do I know it's not -2.1? Could be -2.01. My eyes aren't accurate enough to figure that out. So how do we figure that out with our graphing calculator? And a lot of things that you calculate on your graphic calculator are right here on the calc section button. So to get there, you go second, trace, and that gets you to the calc menu. And we can figure out a whole bunch of things from our graph. In this situation, I'm really interested in this minimum. What's the smallest value it ever gets? So when I push enter, it goes back to my graph, and it says, if you want to find a minimum, we need to know the minimum between which 2 points. Where do you want to find the minimum between? And it starts with my cursor there. I can move my cursor left and right with my arrow keys. And as soon as I push enter, on some calculators it draws a dotted line. On some calculators it just does a little arrow, depending on which version you have. But it says, okay, that's your left side. I want to find the minimum, so I need to go to the right side. And I have two options. I can just either keep hitting my arrow key until I get past it, And as long as I'm past the minimum, I can push enter, because it's going to find the minimum whether you make it really wide or really narrow. Sometimes people are impatient, and they're like, I know that if I hit 3 and push enter, it automatically jumped to 3, saving me that time of hitting the arrow key. For me in particular, sometimes my online calculator, if I hit the arrow button too fast, I crash the system, and that's really annoying. So I sometimes like to use the numbers. It's a little bit quicker to get that range, but it's fine to go left and right. Now between those two lines, is the vertex, is the minimum in between those two? Absolutely. So pushing enter one more time. I don't know why the calculator wants you to guess. It always does this. I'm pretty sure when this comes up, nobody ever goes, I wonder if it's, you just hit enter again, and it finds it at -2. Interesting thing about the calculator here. It's actually perfectly at 1. That point is perfectly at 1 minus 2. You see that my calculator is putting 1.00000021? Some of yours might say exactly 1. Do any of you have another number that's a little bit different? That's also not 1? So, I don't know if this is interesting for you, but what's going on inside the calculator's brain is it actually doesn't have the math skills to figure this out. You guys could complete the square on this one. You could find the vertex perfectly. You have the math skills to do it. The calculator uses an algorithm of checking. It puts in a point and said, did I get smaller? Ooh, I must be closer to the minimum. Checks another point, did I get smaller? I must be closer to the minimum. In fact, there are a whole bunch of different mathematicians that have developed different techniques of getting to the minimum as fast as possible so that computer programs can be faster. So it has a program in place, and once it feels it's close enough, it stops. It felt that 1.0000 is close enough. In reality, the answer is perfectly at 1. So we see that a calculator does have some errors built into it. All right. Type in this next one. First of all, for figuring out the domain, now we've got a place where we could figure out the domain without our calculator. Is everything possible? Well, most things will be, but I'm dividing. And what am I not allowed to divide by? Not allowed to divide by 0. Could the bottom ever be 0? Well, it can't be 0. X squared can't be 9, so that means it can't be either 3 or -3. Those will both be bad. So I could either write it this way, x can't equal plus or minus 3. The interval notation for this is intriguing. If it's everything except for +3 and -3, you could start from negative infinity. You could get to -3 and not include it. Then jump over it and start again at -3 and go to 3 and not include it. Then jump over and start at 3 and go to infinity and put a big U in between each of these. This would be the interval notation form of this. I think I like the can't equal plus or minus 3 a little bit better. But it's going from left to right. You get to 3, you don't include it. That's where that round bracket comes in. Jump, do these ones in between. Jump, do those ones again. Go to your graphing calculator, type this equation in, and see if you can get this graph. I want to talk about possibilities on different people's calculators, depending on which version you have. I'm curious, do anybody's calculators join these together? That's an older version. Does anyone have them that join it? Yours does? Okay. Yours does. So some of the older versions, basically what the calculator is doing is it's doing 1,000,000 points in a row and then connecting them. And they're like, if I do 2 points really close together and connect them, It'll just look like a nice straight line. But what's the problem is that when they did this point, and then connected them, it has that line built in. So if you have one of those older versions, you sort of have to be like, oh, I know there's supposed to be an asymptote there, but I actually join them together. Once I have the graph, it's really easy to see the range is everything. That is not easy to see from the equation. Hello. It is. So it stopped there. And then went way up. Stopped there. That's not bad. Okay, type the next one into your calculator. So to get rid of an equation, you can hit clear. That erases it from before. Square root 9 minus 5x. You notice the question had a t, but we have x. You're okay with that? Letter changing. Also, in any of your calculators, does your screen look completely different? You can set what, like, your graphing calculator has a window of what you're looking through. And you can make that window bigger or smaller or move it around. So if ever your graph doesn't show exactly the same thing, there is a window button right by it, the y equals. If you hit the window button, you can custom make it. Right now, if I hit the window button, it tells me mine was custom made to go from minus 10 to 10 and minus 10 to 10. That is technically the standard window. So you can customize it to whatever you want. I could change this right now to minus 5, and now my graph doesn't go as far to the left because I just went to minus 5. You can also quickly change your window through the zoom menu. I want to go back to what I had originally with that minus 10, but I'm lazy and don't want to hit minus and then a 1 and a 0. That's like 3 buttons. If I go to number 6, standard, 1 button to get back there. I saved about 3 milliseconds of my time. Very good. So you can hit the zoom menu. You can play around with a lot of them. If you ever did stat stuff in chemistry, you might have hit the zoom stat button so that it showed up nicely. When we do sine and cos graphs in radians, sometimes the trig one is really nice. I think it goes from minus 2 pi to 2 pi for you. So there are some zoom ones that are really nice. You can zoom in and zoom out really quickly. And at the bottom, sometimes I like to try the zoom fit. It's basically trying to say, I drew a bunch of graphs. Can you fit them nicely? And then the calculator decides what would be nice. And sometimes it's not bad. And sometimes it's not nice. So those are ones that you can play around with. We've got our standard menu and we've got our graph here. So we need, this is an interesting one, because on our graphing calculator here, to find our range, we need to find a minimum. And I'm going to show you some problematic things that might come up with finding a minimum on this one. So first of all, though, if you wanted to define the domain, we could also technically, if we find the minimum, that will also be the farthest to the right it goes, so that could help us with our domain. But I talked about before, often we can find domain without our calculators. So what do we know about square roots? You can't take the square root of a negative. So this inside the 9 minus 5t has to be bigger than or equal to 0. Can you solve this? Right? And in solving this, you can move the 5t over, or, this is good. How many people, when they solve things, like their variable on the left side? Right? Do you like writing x equals 5 better than writing 5 equals x? Probably. So I can see a bunch of you doing the black. Okay? Now, if I did the blue, I'm going to switch back to blue. Can you see that if you divided by 5, you get 9/5. So our domain, according to the blue, should be that t is less than or equal to 9/5, or you could write it this way, t is less than or equal to 9/5.
I'm in this last.
You're in this one?
Yeah.
Awesome. Here is what you missed yesterday. All the answers are interesting. Those are our notes. Nothing here. So it's like the book. And is someone in this one? Yes. But no one's in this one. You can, and if you don't want to be right in front, no one's in that one. So you can pick one. Okay. Now I'm going to make a mistake. And see if you remember the mathematical rule for making a mistake. I'm just going to divide by a -5. Negative divided by negative is positive. I knew that you thought that was a mistake. But I made a mistake there. And what is that?
When you're dividing by the negative, you have to flip the sign.
Flip that sign and there. Multiplying or dividing by a negative in an equality, you have to flip the sign. That didn't become a problem when we made the 5t positive on the other side, but it did become a problem this way. So we now know that our domain is that t is less than or equal to 9/5. There's the graph that we came up with. Interesting, on that graph, on the graphing calculator, it sure looks like it hits the x-axis. On mine, on the graphing calculator, it doesn't look like it hit the x-axis. Again, little errors that could occur on the graphing calculator. Something I wanted to show you on this one is if I go second calculate and go to the minimum, 3, and I use that as my left, and I type the number 3 on my right, I'm curious if it's going to work. Because do you see that I'm going into some non-permissible stuff? So I'm on my guess. Is this I'm curious, you can try it on yours as well. Does it work? Or does it give you an error? Its algorithm got mad at me because it had to plug in some numbers that didn't exist. So I'm like, oh, I better quit. What can I do? Well, I could, because I figured out the algebra of the 9/5 being the minimum, I can type in 9/5 and find out it is at 0. My minimum button doesn't work here because my graph, you need a right and a left, but on the right-hand side, the numbers don't actually exist, so it causes a problem. So on this one, I had to do a value. Okay, something else we could do on this one if it doesn't work is I could zoom in. So let's see if I zoom in. Oh, it's still not touching. That's interesting. What if I zoom in again? Did it zoom in again? Zoom in. It's not very happy. Oh, it's got a gap. It quit before it was actually done. So sometimes we have a graphing calculator, but we have to realize that it's got an algorithm that isn't necessarily purely mathematical. It's not actually figuring out the math, it's just doing a bunch of calculations, and sometimes it's a little bit off. Okay. So our range on this one is bigger than or equal to 0. And because you could either write an H or you could write look at your equation. It wasn't a y this time. So don't just write y is bigger than or equal to, because that's what you always do for range. Be careful with the variables that are being used. Belle, do you have a calculator today? You can grab one from the suitcase. All right, so type this one in and tell me if you got this as a graph. And this will be a good review of some grade 11 and 12 math for figuring out the domain. See if you can figure, like, there looks like there's some asymptotes, there looks like there's some non-permissible values. Remember, you can't divide by 0. You can't take the square root of a negative number. What would the domain be? I like reminding you of math that you forgot. I feel like there's going to be some good math that you've forgotten in this question that I get to remind you of. How many people have already figured out the values of u that make you divide by 0? What are they? Plus or minus 2. Can you see if you did plus or minus 2, the bottom would be 0 and that would be bad. Technically, if you were drawing this by hand, you would add those in as asymptotes. Now, according to the graph, doesn't it look like nothing exists in between plus or minus 2? But maybe it does way up high or way down low, because we can't see everything. Or does it not exist in the middle? Well, for figuring this out, the bottom part has to be bigger than 0. And I didn't put the equal sign because those are the places that it's equal to 0. But also, the inside of a square root has to be positive. So usually if we just had the square root, we would do greater than or equal to. I took out the equal sign because I knew I also was not allowed to divide by 0. How do we solve inequality equations? You did this in grade 11. And I feel like this is one of the things you may or may not remember. One of the things you can do is you can think of it like an equal sign. And sometimes I even actually temporarily change it to an equal sign, and you would find out the plus 2 and the minus 2. Do you remember making a chart and putting plus 2 and minus 2 on them and then checking which ones worked and which ones didn't? That was grade 11. So I found out where it was equal to 0, negative 2 and 2. Sometimes in grade 11, You even made circles on these values, and sometimes colored them in, and sometimes left them open. The open circle means that they're not allowed either. If you colored them in, then you would have had the equal sign in the equation saying, oh yeah, that it's okay to equal 0, but not okay otherwise. And then, if you test something, like tell me a number bigger than 2. Yeah, pi, thanks a lot. Pi squared is about 9-ish. Minus 4 would be 5. Can I take the square root of 5-ish? Yes. But if I pick something between -2 and 2, and there are nicer numbers, okay, and not nice numbers. A nice number would be 0. A not nice number would be like e divided by 2. I wouldn't pick that. But if I pick 0, I plug 0 in, you see that you're going to get -4. Can you take the square root of -4? No. And if on this number line in grade 11 we learned, if you found one point in that section to be false, everything in that section is going to be false. Right? If I plug in 1, sure enough, I get -3. It doesn't work. -1, -3 again. It doesn't work. So everything in this section is false. And if I plug in -3, well, -3 squared will be 9. I get 5 again. Perfect. This section will all be true. And then when we go to write our domain is that the u values have to be less than -2, or our u values have to be bigger than 2. We could write it this way as well. And our range. How do we find out that there is, sure looks like there's an asymptote here at 3 and at -3. How can we find that out? Using our graphing calculator. And I'll also show you somewhat how to find it out mentally thinking, because I want to review you of something. You saw horizontal asymptotes in grade 12 pre-calculus with rational equations. One of the things you might have seen here, if I had this equation, do you remember that you could find out that your horizontal asymptote was at y = 3 because there is the same power of x, like x to the 1 and x to the 1 here, and you just look at the x's, and 3x over x is close to 3. And the idea behind a horizontal asymptote is that they show you what happens at extremes. So at extremes, adding 7 really no longer matters, right? Right? If I phone up Elon Musk and say, hey, I'd like to meet you at the Forks, I'd like to give you $7. I don't think he'll show up. If I told some of you guys, I'm going to be at the Forks on the weekend, Saturday at 2 o'clock, meet me in front of the museum and I'll give you $7, I'm sure some of you would show up. Elon Musk is not going to show up because he has a lot of money. Is $7 going to really make a difference to him? No. And as things get really, really big, that +7 becomes less and less important. And so then we would just say, well, if I ignore that, 3x over x, it's going to get really close to 3. Like 3 million divided by 1 million plus 7 is really close to 3. So we have extremes here. Why does it become 3 and -3 here? Well, technically, if I ignore the 4, what's the square root of u? It's just u, right? And then I would have -3u over u, which is -3, which explains the 1 at the bottom. Why would there also be 1 at the top of 3? Well, technically, u squared, the u could have been a negative number, right? Because a negative number squared is still positive. That still exists. So sometimes when I square root this u squared, the u was a positive number. And sometimes when I square root that u squared, it's a negative number. So it could be sometimes 3 and sometimes negative 3. That's some complicated stuff that we get into details later on. But that explains why our range is not this. Our range goes from, we could write it like this, y is less than negative 3 or y is bigger than. Awesome. Okay, so there's some graphing calculator stuff, and touched on this very briefly in grade 12, but we're going to look at piecewise functions. And the absolute value function, so you have to write that in, f of x is the absolute value of x. Do you remember the absolute value graph looking like this? It's a V-shaped kind of thing. And the absolute value graph is basically 2 lines glued together. And you know how to find equations of lines, y equals mx plus b. In fact, this part, which I'll change colors here, I'll make that part green. That part is just the line y equals x. The blue part is y equals negative x. A piecewise function says sometimes if you see a graph has 2 parts that you could get the equation of both parts separately, you can write it as 2 different parts. And then when you write one part, you then explain its domain. We have the green part just when x is bigger than or equal to 0. And we have the blue part when x is less than 0. And generally, I have the equal sign with one and not the other. It didn't matter which one I had the equal sign on, but you can't say it's 2 equations at the same time. You have to pick one to have the equal and one not. So we have 2 equations. This makes this a piecewise function. So if you do have a piecewise function, and we're going to graph a couple here, you can sketch each piece separately. And I'm going to color code them here. I made a table of values. I don't think you need to make a table of values for g of x equals negative 6. Because it's like, what happens if I plug in negative 2? I get negative 6. What happens if I plug in negative 3? I get negative 6. What happens if I plug in negative 4? I get negative 6. Surprise, surprise, the equation is always negative 6. X plus 1 to the 4. Well, I could get some values that way by plugging them in. And we're going to find out here, see, this one has a less than sign. That means at that starting point, it's going to be an open circle because it's not included in that equation. And on the other piece, because I have the equal sign, that one's going to be a closed circle. So when I put both of those graphs together, y equals negative 6 is just a straight horizontal line, but it has an open circle. And then the x to the 4 graph, quartic graph, kind of parabola-like. And this is the final graph. It just has 2 completely separate pieces that aren't related to each other at all. And so there's not a single equation that makes this work. You could probably get AI to take a picture of your face and draw it with circles and lines and come up with this huge piecewise function. And this is the function of my face. And it would draw it probably pretty accurately. That's pretty cool. Rather than me in the past thinking, oh, I should spend hours and hours doing this. No, that would not be a very good use of time. All right, let's look at the next one. Again, this one has 3 pieces. I color-coded it purple, green, and black. The purple one will have a closed circle at -2. The green one will have 2 open circles. And the black one will have a closed circle. The little table of values probably don't need, do you see that they're all straight lines? Many of you could probably go right away to graphing these. This one's always going to be -4, straight horizontal line. X -2 has a y-intercept of 2 and a slope of 1. But I put a bunch of points in anyways. And -2x plus 4 has a slope of -2 and a y-intercept of 4. When we graph all of those together, technically we would have had an open circle here and an open circle there. And on my purple graph, this would have been filled in. And on my black graph, this would have been filled in. So my 3 lines were put together, but it ended up making a graph that's all continuous, because where the green graph ended and there was an open circle, the purple graph filled it in. And on the other side, the black graph filled it in. And the last piecewise question. Now you have the graph. Can you come up with equations of all 3 parts? Here are the handouts. Also, handouts in this. We have weekly assignments. The first one's due next Friday. Formula sheets from grade 10, 11, and 12. That can help you, but you don't get a formula sheet for this course on the exam. I'm going to just post the course outline for this one on Teams. All right, I'm going to put up the answers, see how you did. Did you get that the straight line part was at 2? And we can't have an equal sign there because of the open circle. Next one had a slope of -1 and a y-intercept of -2. So -x minus 2. And it happened between -4 and 2. And because there are open circles on both sides, no equal signs. And finally, the last one had a slope of 1. If you extended it, you probably can see that the y-intercept is -6. Also no equal sign because of the open circle. last topic we're going to look at today is even and odd functions. And you saw this already in grade 12, and we mainly looked at it with polynomial functions. Whenever you had an y equals x and the exponent was even, like y equals x squared, y equals x4, y equals x6, those are all examples of, surprise, surprise, even functions. And every time that that exponent was odd, y equals x cubed, x to the 5, x to the 7, surprise to surprise, those are all examples of odd functions. But what is the exact definition of them? Well, a function is even if every time you plug in a negative x, it's the same as plugging in an x. For example, x squared. Plug in 2, you get 4. What happens if you plug in negative 2? You still get 4. Graphically, even functions are a nice reflection over the y-axis. If you take half of it, reflect it over the y-axis, and it matches the other half, you have an even function. So not all parabolas are even functions, because if I take the x squared graph and move it 2 to the left, it's no longer an even function because it doesn't reflect nicely over from one side to the other. It has to reflect perfectly over the y-axis. So we say it's symmetric with the y-axis. So here's our graph of our parabola. If you take either half of it and flip it over the y-axis, it matches up with the other half. How do we show that algebraically? So if they say, prove something is even, the definition of proving something is even is right here algebraically. You need to show that f of x and f of negative x are exactly the same. Well, we already know what f of x is. It's x squared. So algebraically, we look at, well, what would happen if I do f of negative x? And function notation, which we were practicing yesterday, says you're now going to replace each x with the negative x. And negative x, put it in brackets, when you square it, just becomes x squared. So f of x is also x squared, and we can say that what we want to prove algebraically is true. It is even. It is symmetrical about the y-axis. Yeah, I work your brain a little bit right now. Are you ready to have your brain work a little bit? I want you to think back to all 6 trig functions. Sine, y equals sine x, y equals cos x, y equals tan x, y equals secant x, y equals cosecant x, and y equals cotangent x. Which ones are even? Which graph can you flip over and match up the other one? How many of them are even? There is one. There's at least one. Can you remember your basic sine, cos, tan graphs? So I said I'm going to make your brain hurt a little bit. Cos, right? Because cos starts at the maximum, and if you flip it over, it makes perfect. Are there any more?
The inverse of cos?
The inverse or the reciprocal. Here's a great French thing. Did you know that inverse in French is réciproque? And reciprocal in French is inverse? Like, what were they thinking when they translated that? I'm telling you, someone screwed up somewhere. They've actually done history of math screw-ups. And they happen in, often it's happened in translations. So, you know what a trapezoid is? That's actually the wrong word historically. A trapezoid's historical word originally was trapezium. but some American author translated a book and translated the word wrong. And then his textbook got used a lot, so much that there was all of a sudden English textbooks coming out of Great Britain that didn't match what was happening in English textbooks coming out of the United States. So there was a little bit of like a fight for a while, and then they're like, okay, we'll go with trapezoid. Even though it was the wrong word originally, it started getting used more, and so now we don't talk about trapeziums anymore. So I think something happened somewhere French and English, I'm not sure. But the reciprocal of cos, the secant graph, is also an even function. Odd. I sometimes think of odd functions as a double reflection, because technically I could take this and I could get f of x is equal to move the negative over to the other side and have both reflections on the other side. That's perfectly fine. That double reflection, we sometimes say it's symmetrical with respect to the origin. You take any point, draw a straight line to the origin, and then go straight line in the same direction and the other way, and if you hit the graph again, it's symmetrical in the origin. But the double reflection is an easy way to kind of visualize it, right? If I take this half here, and I can choose which reflection. If I reflect it left first, it becomes this. Then I reflect it down, it matches up perfectly. It's going to be an odd function. If I take a point, go straight to the origin, and then take that same distance to the other side, and it matches up, that's what it means to be symmetric with respect to the origin. So usually if we're trying to prove even or odd, we start with trying to prove even. So we'd start with the negative x inside. I put the negative x inside, I cube it, and I get negative x cubed. Did I get x cubed? No. It's not even. Because if it matched up perfectly with the original one, that's the definition of even. So if it doesn't, then I could try the other one, negative f of x, and see what happens if you put the negative out in front. Sure enough, you get negative x cubed. So these two match up, and it is odd. So again, to prove something is odd algebraically, you need to show this. So often you can see even and odd quickly from a graphing calculator. And if you know something is even or odd, you can do some algebraic kind of manipulation stuff with it, which is kind of cool. Okay? But each of these, if you graph them on your graphing calculator, you can probably tell right away. On your graphing calculator, even, odd, or neither, you take half of it and flip it over and match it up? Yes. So this is going to be even. If we want to show it algebraically, then we would say, I'm going to check f of negative x, plug in that negative x, and see if I get the equation that I started with. I do, which I could already tell from my graph. So I would know that it's even. While you're writing that down, just in case you want to work ahead, you're going to get lots of take-home quizzes this year. That is a true statement. You could either get them early, or I could give them to you right before their due date. That doesn't matter to me. This one's I'm giving to you really early. I think you prefer to get them early, rather than the day before a due date. Some of you like to work ahead. Some of you work best under extreme procrastination situations. If you're in an extreme procrastination situation, this is you on Monday. But if that motivates you to start it this weekend, perfect. A lot of this stuff is review from grades 10, 11, and 12. So you definitely, like, sometimes I could give you really early your first take-home quiz for derivatives, and you would have no idea what's going on whatsoever. That would not be very helpful. But this one, I can give to you early. It'll be due sometime next week, but we haven't decided yet. But apparently in Mr. LaFrance's class, some people have already finished lab 1. People already finished lab number 1 in this class. Couple. Okay. So, you can also work ahead on your labs. Take advantage maybe of certain times in the year when you're not busy with a whole bunch of stuff. May as well get started on stuff that you're going to do anyways. All right, we got 2 more graphs. Here's 2x over x squared minus 3. I typed that into my calculator, and it's definitely not even. It's really easy to see even ones quick, yes or no. Odd ones a little bit trickier. But again, if you take half the graph and do a double flip, does it match up? Yes. So it looks like it's even. So if I want to prove even algebraically, I need to find out what g of negative x is. And simplify it. Again, I could already tell that it's not even after that stage. And that's why it's always good to start with plugging in the negative x if you want to prove it algebraically. Because if you get it to work out, you know that it's even and you don't have to do any more work. But when I put the negative out in front, it matches up perfectly. So I know that this one is odd. So on all of these things, if you're curious what the graph looks like, please use your graphing calculator. Or if you're working at home, download the Desmos app and also play around with, how do I do this on Desmos? Because there are some things that are way better in your graphing calculator, and there are some things that are way better on Desmos. And you have access to both on your exam. So if you're like, ooh, I know how to find an x-intercept super fast on Desmos, get to know that, because it might be quicker than your graphing calculator. But there'll be some things like, do I know how to type this into Desmos? So I know how to type it into my graphing calculator, but do I also know? And that just comes with practice and playing around. And our last example, oh, I don't. Do I not have the graph on this one? I guess I don't, so we have to do it algebraically. I would start with h of negative x. When it gets cubed, that negative stays. That doesn't equal the original. I know that it's not even. Next, I would put the negative out in front. And now I have to sort of like, how do I know for sure that these are either, maybe these aren't the same, because they don't look the same right now, right? Like I have a negative out in front, the other one doesn't have a negative out in front. Are these the same or different? How do I deal with that? Method 1, I put the negative inside. Does it make sense that a negative 1 is the same thing as the cube root of negative 1? And if I have radicals that are the same index, the same cube root thing, then I can put them together and this becomes 5x cubed plus 1. So that's me putting the negative inside. They don't match up. It's not odd. I could also, and I'll show you here, I could have also played with this one. I could have played with this one by factoring, oh, almost, wait for it, there we go. Factoring out the negative 1. And then multiplication, I could break this up to pull the negative 1 out in front and then see that they don't match. So this one is neither odd nor even. Happy first week of math.